current carrying conductor in a magnetic field. Got it?
No.
So
Now, come on, it's like 6 words. Oh well, in that case, take your time. Now?
Yeah.
Okay. Couple of equations to do. Okay, Sean. So, yesterday we saw the left-hand rule. And if we look at this picture, we can see the left-hand rule again. Here is the field from north to south, so the finger points this way. Here is the current running left to right. Current runs this way. So there's a force acting up. And this we know from yesterday. Nothing new here. So a charge moving in a magnetic field will experience a force. What about a current? Well, a current is just charge per time. So also a current will experience a force. So the question now is, what is the force that the current will experience? So if you just think about from yesterday, how much did we say the force would be for a charge Q?
QVB.
QVB, yeah. Yeah, so let's have a look here. Excuse me while I just turn my pad on. Come on. Don't be a jerk. No, it's not dead, because it has light. There we go. Still going. Okay, so here is our current. And let's imagine here's the charge, and the charge is moving along here. And we said that current, remember, is Q over T, or delta Q over delta T. So there'll be a force up here, and we know that the force equals Q V B. That's fine. But we don't have Q here. We only know what I is. So if we know the I, we can just say the Q is IT, like this. Yeah? Okay, so if I just put that back in here, that's Q, T, B, B. Yeah, that's it. Oh, sorry. Q, what am I saying? Yeah, not Q, sorry. I, T, B, B. Now, actually, this means something here. If you think about the triangle, distance, speed and time. Time multiplied by speed, the distance. So the distance, of course, is how far the charge moves, which actually is the length of the wire, the L. So that's ILB, or just Bill. Bill, yeah. This is the force on a current in the magnetic field. You know Bill?
Yes.
He's a friend of yours? Who's Bill?
Bill Clinton. Am I right?
There's Bill Clinton, there's Bill Gates,
Bill Clinton.
Bill Cosby.
Bill Gates.
You don't know Bill Clinton?
No.
Husband of Hillary.
I just realised that those 3 Bills, Bill Clinton, Bill Cosby and Bill Gates, at least 2 of them are sexual offenders. It doesn't seem to be good to be called a Bill. No. It's 2 L's, correct, yeah. So I guess if it's 1 L, that's okay. Okay, continue. You got that formula?
No.
No, okay. You probably have seen this formula before. Yeah. No? Okay. Not too difficult, right? Continue. I still see people writing. No, wait. Is just Bruce writing?
Just try the line.
Can I continue?
Yeah.
Okay. So, we have our formula, F equals built. In this formula, the current is perpendicular to the field. If it's not perpendicular, that is, if there's angle theta, then what would the formula be? So in this picture, maybe to draw it again here, let's see, what it was like north here, wasn't it? South here. The field runs this way, and the current was going this way here. This isn't. Let me try and draw this a bit more three-dimensionally. Current going this way, and then into the page is the field, and that's perpendicular to it. And then the result is the force acts upwards here equal to BIL. Isn't that right? Where this is B and this one here is I. Let's just double check that. Yeah, that's right. That's right. But now suppose instead of being perpendicular, it was at an angle of theta. So in other words, let me just take this red line again, or the blue line. So right now it makes an angle 90 here and here. Let's imagine instead we draw it at an angle like this. So instead of being 90, it's theta. So what do? Well, we resolve it. Yeah, so in this one we say there is an this one's sine theta. Yeah, and because this one is this side is touching the angle, this side here is I cos theta. Now, both these wires, or both these components, you might think have a force. There could be a force acting on the, we think, but obviously we know it's not, because I'll explain in a moment. We think there might be a force here and a force here. But there's actually no force here in this direction. It's still only here in the perpendicular. Because when you use this rule here, you can't have the B and the I in the same direction using this rule. They have to be perpendicular. So here, this B and this I cos, they're in the same direction, which is impossible. It has to be perpendicular. So you get everything only from this. Only this component matters. So in this picture here, F would be equal to BIL sine theta. And please note, this makes perfect sense because if theta equals 90 degrees, then it goes back to being BIL. So this is if they make an angle of theta, the current and the field, an angle theta between them. We have this formula. Okay, so obviously should write this one down.
From the eye.
What do you mean?
From
Huh? Well, the angle's here. So which angle are you talking about? That's the one we care about most. I think that's okay. Where have you seen something like this before where you only care about one of the components? Do you remember? In mechanics, somewhere in mechanics.
Yeah.
Turning force. Remember for turning force, you don't care about the component that goes through the turning point, only the one that's perpendicular. Kind of the same thing here. Alright. So we have our Bill sine theta formula now, which is good. Okay. If a force acts on a current in a magnetic field, then could we use this force to do work? In other words, could we use the formula? We could. You don't think so?
Huh?
I think yes we can. So we can use something called a DC motor. Look here what happens. A current from the positive runs along this conductor here. Now if we look here, let's figure out the force. So the field, which way is it going? To the right. And the current is going in. No, hang on. The field's going that way. The current's going in, so the force is going up. If we look at the other end, the current is going to U, the field is going that way, so the force is going down. What will happen to this wheel? Well, it will start to turn. So we can actually have like an electric car, moving the wheel. Now it's important though, this here is connected in a very special way. These wires they're not actually attached. This here is a brush. It's a brush that just is against the wheel. Now why do you think we have a brush touching the wheel instead of having the wire connected? To allow it to rotate, because if the wire was connected, then it would get tangled up. But if we have a brush, then we can still have the current connected, but it won't get tied up. So these are usually made of carbon, because carbon's a good conductor. So these are usually carbon brushes. This actual special connection is called a commuter segment. This one here. Now it is normal enough, like maybe in 20% of the exams or 15% of the exams, they ask you to draw the DC motor. Yes. So you get marks obviously for having the right parts. What are the parts you need for the motor? We need a magnetic field, we need the commuter segment, we need a power supply, and we need this piece here which is called the armature. It's just the name of this piece.
When we drive the cross in the exam, should we write the name?
Yes. These names. Well, you don't need to write south and north because you wrote S and N, so it's obvious. Yeah. So I'm afraid you're going to have to draw this down. Yeah.
Can't see the more.
I'll turn the light off.
So what is that component?
Commuter segment.
Segment. not doing to memory.
All of it.
Include that brush.
Yes, including the brush. Did you draw it, Bruce?
Yes, I right.
Please write the names.
Because I
Can't see it.
just feel it. You know, my eyes are
Okay.
Ah, so perfect.
Yeah, let's see. Wow. It's like I'm looking at real life. Okay.
It's not perfect.
You have
Throw the
feet?
Flux.
True. Okay, continue now. I'm sorry, I really need to continue. If you have to finish this drawing later, then you have to finish it later. But I can't stay here too long looking at this picture.
Fine.
How much have you left to draw? The names. Do you have the names written down, Lee?
Yeah.
Yeah, so you can give them then. Okay, let's find a formula for the torque, the turning force of the wheel. Okay, so here is the roughly the armature, and it's spinning around like this because there are two forces here. One force this way, or rather maybe I should say one force here and one force here. Now, you have to really think back to mechanics. We're looking for the turning force here, the torque. What type of problem is this? We've seen this in, like with the steering wheel. What was this called? No, the name of this system. No. This is actually a couple. Do you remember this? Where you have this and this and a distance between them. We did this, it's called couple. So the turning force is just Fd. Yeah. But what's F? Well, F is BILD. And this side here is the L, and this side here is the D. So what's L multiplied by D? It's area. It's this area. Now, if you want to make the torque greater, a trick you can do is this. You can have the wire go around, but then have another one go around. So you would have maybe two forces. And then you could have another wire. So you could wrap the wires around a few times. So let's say we wrap it around n times. What happens to the force? It becomes n of them, which here means basically we get an n. So the turning force is equal to I ban. Yep, like the bank.
Teacher,
Yeah.
the L is just not the whole armature.
The L is just the length of the wire.
Yeah, but it's a whole armature, right? Like a
No, it's not actually, because remember, this part here we don't care about because it has no force. So the length is actually, it's irrelevant because there is no action happening here. Neither is there any action happening here. It's just this piece, and we have two of them. Yeah, so it's not the perimeter L, it's the length of one of the sides. Did your teacher in high school tell you it was the perimeter?
no, we didn't study this.
Oh, okay. Anyways, IBAN is the turning force here, the torque.
Teacher,
The white.
it's a pattern of
Yeah, the number of turns. Yeah. So like, this would be maybe n is 1, but if you can have the wire go around twice, then that's n is 2. Got that? Yeah? Can I continue, please? Yeah.
Sigmund,
Yes.
if we wind twice, then
Yeah.
how much? Would it be twice?
Twice the force.
No, battery current.
I don't think so. No, I don't think so. Now, I don't really know, because there must be some price you pay for having the wire wrapped around twice. Perhaps the price you pay is it becomes less efficient because there's more heat, because there's more of a conductor. So perhaps although the force might increase, it might become a less efficient motor. I don't know actually. That would be my guess, because conductors produce heat. If you double the wire, you double the resistance, which means you double the heat, which means you make it more inefficient. So I would guess that would be the price you pay. Okay, continue. Yep. So this is our formula for torque, turning force, IBAN. Now, recall that the flux over some region of space is the number of field lines. And what unit did we use to count the field lines? WB, Weber, yeah. However, imagine now that the field passes through n identical regions we're interested in. Let us find a formula for the total flux. So what I mean is, remember last time we said here is a region and here is 1 Weber. So here we say the flux here is 1 Weber, like that. But let's imagine that we have maybe 3 of these regions. So what is the total flux here? Well, the total flux will be 3 Webers, because it passes through 3 times. No? You look a bit confused. Imagine I have this, and I have one go through here and one go through here. What's that? 2 Webers, because it hits the region twice. Now imagine I have this. It goes through here, and then there's one that goes through here. What's that? 2 Webers. Now suppose I have one that passes through here, and then passes through again. It's still 2. And they don't have to be connected. I never said in the definition that it has to be connected. You could have it like this, 1, and here, that's 1 Weber for both of these. So here it's 3 Webers, because a field line passes through the space 3 times, in 3 places. It passes here, and passes here.
Weber is just the pass time.
Huh? It's 1, but it passes through 3 times. So we actually say that's, in total, 3 Webers. Yeah? This is what I mean when I say the total flux. The total flux. In other words, it's just, if you have here n spaces, the answer will just be n times the flux for 1. That's all I'm saying here. That's all. So here, it will be n times the flux, MBA. But remember, we have this formula. Come on. Remember, we have B equals flux over area. So if I put that in there, I can get NBA. MBA, yeah. So this is the total flux formula. Yeah. In those 3 parts, for example, yeah.
to be able to do.
They have to be, the reasons have to be identical, yeah. Can I continue? Now, what if the field makes an angle theta with the normal of the space? Now I have to draw that carefully. So, here is the space, and here is the field, and this will be 1 Weber. And the angle, we want to change it. Now, for these problems, the way you measure the angle is between the field, obviously, and you might think it's between this line here, like that. It's actually not. You measure it between the field, right, have that coming out here, and the normal. The normal, remember, a bit like with normal and tangent in maths, the normal is the line that's perpendicular to the space. So at the moment here, the theta is 0 degrees, because the field and the normal, they're parallel. But then what happens if you change the angle a little bit? So let's say we have the field and it goes this way, an angle. There's a theta between the two. Well, again, we resolve. So this one here, this would be, for example, 1 Weber cos theta, and this one here will be 1 Weber sine theta, or rather, perhaps I should say the flux cos theta, and this one here will be the flux sine theta. Now, which one do you care about here when you want to know the flux in total? Yeah, because it's the one that passes through it. The other one actually doesn't pass through it. Only the cos one does. So you realise, oh, like earlier today, all I have to do if there's an angle is just stick a cos theta at the end. And that is the flux at an angle in total. Who?
Isabel.
Isabel? Yes, I saw her this morning. Yeah. Why, is this good or bad news?
No, I mean, she didn't send us any mail, email about the indicators.
What time is that at?
That's all.
Oh, you might have an email after this class.
I don't know.
As you wish. Okay, finally for this slide, the total flux is also called, there's another name for it, magnetic flux linkage. So if you see that in the exam, it means they want the total flux, mostly. There's actually a small difference, but that's not important for us. That's your breakfast, Bruce.
Yeah.
4 of them. Healthy.
Wow, it's mine.
Huh? I'm just jealous. No, go ahead, have one.
I just pulled it.
Oh, okay.
I'm happy.
Thank you.
He's so kind, isn't he? He's so kind.
You have helped me to eat.
Yeah.
Always,
Okay.
it's like you.
Yes. Well, I'm kind
They
too.
can share everything.
Yes, indeed.
He
Mm.
can share with me. Share with you.
You're so generous, so generous. Okay, you got that?
Yeah.
Magnetic flux linkage means total flux.
If it is more electric, that means it's more fast.
Yeah. More current means it should spin faster. Yeah.
Like car horsepower.
Yeah. You could work out the horsepower. It would be. It should be related to the current. But the problem, as I was saying to KJ, is as the current increases, the heat also increases. So it would make a lot of heat in the engine.
It will have a speed limit, like
Oh yeah, there will be some kind of limit. Yeah, I don't know what it is for a car, for an electric car, but it would have some rotation limit. Yeah. Okay, here's our first example. A copper wire carries 2 amps of current. The copper runs through a magnetic field so that the copper is perpendicular to the field. The copper is 20 centimeters long and the field has a flux density 3 Tesla. What is the force acting on the copper? So have a look at your formulas and decide which one this is that you need for this one.
B-I-F-L.
Yes.
field.
You said that so dramatically. B-I.
I'm not sure.
Yeah, you're right. You're right. So what's the B here?
3.
3. And what's the I? 2. And the L?
0.2.
0.2. So it's 1.2 newtons, is that right? No, it's 1 newton. No, 6. Yeah, 1.2 newtons.
Yeah.
No. So just multiply 2 by 3 by 0.2. That's all you have to do. The next one is, what if the copper makes... Bruce!
Yeah.
Next part, tell me, Bruce, since you know everything. What do we do for part B if the angle is 80? You're not Bruce. Go on.
What about cosine?
By cos or sine? Have a look at the formula. I think I said it's sine. Right?
Yes.
Okay, I read it wrong.
Yes, you were, Bruce, believe it or not. So, this is the answer now, 1.18. If you can write that down, please.
Teacher, now the A means current.
I means current.
I means current.
Oh, A, the unit means amps. Yeah.
How about B-I?
A is for area.
Area.
Yeah. Continue, next one. That was a short one. A DC motor is used to turn a wheel. A current of 3 amps runs through the DC motor. The flux density is 5. The wire runs 1,000 times around a square of length 20. What is the torque? Okay, which formula is this? No, this isn't, Bill. I want to know the torque of the wheel, the turning force of the wheel. This is I-band. I-band. What's the I? 3. What's the B? 5. What's the A?
0.0.
Squared.
Oh,
Yeah? And what's the N?
1 ton.
So the turning force of the wheel is 600 Newton meters. The turning force of the wheel, 600 Newton meters. What's wrong? Is it? 600 Newton meters is the answer here.
Teacher, well, we have it school exactly. Teacher, I saw semester 1 students, they have physics book. We do not have. It's not fair.
I can print you out the semester 1 physics book if you want to keep that. No, if you want that for notes.
Teacher, I lost that sugar.
There's a problem.
Wow.
The problem is I haven't made it yet. So I can't print it out. semester 2 book.
We need a book. We need a book.
You don't need book. The only thing that the book is the questions I have at the end of the lesson.
Yeah, we need that.
Yeah.
I know it'd be convenient to have the book, but you still have the questions. They're at the end of each lesson.
Could you make that?
What?
Could you make a book of the past exam?
This is on my to-do list, but this will come after the workbook of questions. What's Newton meter for turning force?
Is it Joe?
It's also joule, but we don't use joule when we're talking about turning force. We say Newton meter. Remember, turning force is force by distance. Yeah.
How it works? Wow.
What?
For my lesson. I can like how this can work.
What do you mean? I'm totally confused by your question. KJ, what's the definition of turning force? Force by distance. You know, distance, force. What unit is this? Newton. And what unit is this? Meter.
But in your life.
What do you mean in real life? This is real life.
Oh, I know it. It's Star Wars. I know it's
Where? Real life.
I know.
He's lifting up a pole.
That was the movie.
Yeah.
I know it's famous.
Yeah, that was the movie.
But it's too old for me.
Continue. By the way, Star Wars is garbage. Continuing.
Garbage.
Like
Trash.
we'll say that to find out.
Garbage.
Garbage.
What's the garbage?
Trash.
Trash.
Yo.
I know it. Why does it?
What?
Why?
Just is.
Oh.
Okay. Can you try this one now? Because I've done 2 for you. Try this one. I'll draw it for you. A coil is wrapped around an iron rod 100 times. So you have some iron. And its radius is 5 centimeters. And you wrap around it 100 times. A magnetic field runs from the top of the bottom, from top to the bottom of the iron core, so that the core and the field are parallel. The flux density through the iron is 2. So there's a, what do we say? 2 Tesla is the B. And what do I want? What is the flux linkage? So what's the formula for the total flux here? NBA. Now the area here is actually, there's actually 100 circles.
105.
Yeah. Yeah. So the total flux linkage is 100 times 2 times
0.05.
no.
2
Tesla.
100.
Pi 0.5 square.
Not 5 squared.
Why is the R?
0.
Are we happy that this is the N? This is N. Yeah, this is the N. And this is the B. Yeah.
This is A.
So what's the A?
Pi.
Pi or squared? It's a circle.
Pi squared.
Huh?
Two times 1.
No, the 100's already here. One. 1.57 Webers. What's wrong, Sean?
Why do we care about
What do you mean, why do we care?
the strength?
Yeah. Bigger the Weber, bigger the force. Because the bigger the Weber, the bigger the B. The bigger the B, the bigger the bill. The bigger the bill, the bigger the force. So the bigger the force, the harder they fall. Okay, the next part here. If instead the field makes an angle of 10 degrees, so if I just slightly move this over 10 degrees, well, what's the only difference? Yeah, cos 10 degrees. So, just multiply this answer by cos of 10. 1.55 would be the answer if it was at 80 degrees. At 10 degrees. Yeah.
Teacher, how kind of it's cosine
The formula. Now the good news is,
it's always cosine.
yeah, the good news is the way they do these questions in the exam is when they give you the angle, you look at the formula, and if you forgot if it's cos or sine, it's in the book. So you don't even have to think about it. You just look in the formula book, and it will have cos or sine in it for you. There's no thinking.
Yeah, good.
Yeah, thinking bad. Yeah.
Memorize. It's also bad.
Yes. So memorize bad, thinking bad. You don't have to memorize the formula. It's in the book. You don't have to think about it. Yes.
Formula book.
Formula book. Yeah.
Picture is bad.
What?
Teacher is
Picture. Not picture, it's picture.
What about the picture?
It's
changing.
as all.
But it's not gonna be in day one. I mean, deeper no. You have to.
Which one? Oh, the picture.
Yeah, the picture.
Oh no. In the exam they might give you a picture.
He's talking about this motor.
Oh, the DC motor. No. This you must memorize. Okay. Right. So here we go. If you want to take a picture on your phone.
We can have business share.
Look.
You
don't-
have water sheets, okay.
Yes, and I will print them, I promise. But you must understand how busy I am this week.
But it's okay that just upload the model.
Yeah.
I will upload, I think they're already on Moodle, but I don't know if they're up to date. I'll have to re-upload the slides.
Oh, you mean the file, I mean the only.
It's a long,
No, on Moodle
long
I have uploaded the last slide.
ago.
Oh, really?
I think so.
It's a long.
But I would prefer to print it out for you.
And
Not the picture.
The math I promised next week, and I know I definitely can do that because I already have the book made. You don't understand how busy I am.
Are you done?
I don't
Are you
understand.
done with your coursework? It's due.
How many maths teachers are there?
You.
And 2 more. Yeah? But whose maths book do they use?
You.
Everybody needs me.
Everybody
Everybody needs me, and everybody wants something from me. I have so little time. The teachers want something from me, a principal wants stuff from me, my wife wants stuff from me, just everybody, students want stuff from me. I so little time.
It's only no one shoot. You don't have a shoot.
Yeah, no capacity.
Because you already have a